In this lecture, I shall discuss about the dielectric property in nanomaterial. So first of all, we know the dielectrics are basically materials having very high band gap, so that the electrons from the valence band cannot be excited to the conduction band. So the electrical conductivity is almost zero. So these are what is called dielectric materials, and the electrons are very tightly bound with the atoms itself. Now in studying the dielectric material, mainly we shall deal with the frequency dependent dielectric constant, etc. Usually the dielectric property is independent on the strength of the electric field, but it depends on the frequency of the applied AC electric field. Usually in semiconducting oxides like zinc oxide, titanium oxides, etc., the dielectric constant is strongly dependent on the frequency. And several other materials, usually metal oxides, these are mainly used in several optoelectronic devices. So understanding their dielectric property is very much essential. To study the optical property of any material, we have to understand its dielectric constant, which is directly related to the refractive index and the extinction coefficient K, and they are connected by this equation, the square root of the dielectric constant, which is refractive index, which has the real part and the imaginary part. This imaginary part we are saying as the extinction coefficient, and these are the connecting relations. Again, this dielectric constant is frequency dependent, as you have already mentioned, and it is complex in nature, so that it can be separated out into two parts. One is the real component, and the second one, epsilon 2, is the imaginary component, and both these epsilon 1 and epsilon 2 depends on the frequency of the applied field. So we want to understand this frequency dependence of this dielectric constant. So the very common proposed model is classical model is the Lorentz, Rode and Sommerfeld model, and in this model, electrons near the conduction band edge contributes to both the N and K, the refractive index and the extinction coefficient. So these electrons contributes to the dielectric constant epsilon. So considering the classical theory for these free electrons, the equation of motion can be written as this one. The applied electric field, externally applied electric field, is E equal to 0 e to the power I minus I omega t, and R is the relative displacement of the electron. So we have the general equation: inertia force is equal to the externally applied force due to electric field minus E times the electric field, and the damping force minus tau into dr dt. This is very common equation in classical mechanics that you have already learned. So here this tau represents the phenomenological damping constant, and this mass is the effective mass of the electron. Now as the effective mass of electron is very low, they can obviously follow the external frequency of the external electric field. So we can write the frequency dependent position vector as a solution for this equation as R equal to R0 e to the power minus I omega t. Using this trial solution in this equation, we can readily emerge out with this, which finally yields the value of R0 as this one. So that R0 equal to this. Okay, this should not be there. So R0 equal to E0 by m into omega square I omega tau. This R0 should not be here. There is a typological mistakes. Okay. So now, since we have got this relative displacement R0, and then if n represents the number of electrons per unit volume, then minus n E0 and R represents the dipole moment developed per unit volume, because this minus E into R0 is the dipole moment and n is the number of charge per unit volume. So minus n E into R0 is the dipole moment developed per unit volume, which is known as dielectric polarization vector P. So this P equal to minus n E R0, and using the previous value of R0 we arrived at this equation. Okay. Now we know a very common relation with the dielectric constant, polarization vector and electric field as D equal to epsilon E equal to epsilon 0 E plus P. From here we find this epsilon equal to 1 plus P by epsilon 0 into E. And following this expression from this P by E, using this equation, this P by E, we can write this epsilon equal to this one. And we do a little bit of calculations, like and we take omega square equal to n E square by epsilon 0 m effective, we write this one. This omega p is known as the plasma frequency, which basically represents the collective oscillations of the wave. Now consider the case when the damping is very small. Under damping, small damping, that is tau is much less than omega, or omega is much greater than tau, we can approximate epsilon 1 as 1 minus omega p square by omega square, and epsilon 2 is equal to omega p square by omega cube into tau. So here is we find an approximate 1 by omega square variation, and here in case of complex part we found omega 1 by omega cube relation. Okay. So for the free electrons in the bulk system, they moves with the Fermi velocity Vf, and let L be the mean free path. Then its damping constant can be represented as tau equal to this Vf by L. As you know, this damping arises only mainly due to the scattering of electrons from several defects, impurity and lattice imperfections. However, in case of nanostructure, the particle size being very small, the lattice periodicity is lost due to these broken bonds. So the electrons within the nanostructure will get scattered from the surface of the nanoparticles, and if d be the diameter of the nanoparticles, then the damping constant in case of nanostructure, the surface scattering, can be represented as tau s equal to AVF by d, where this A is taken as a proportionality constant. Hence, in the damping there will be two contribution, this intrinsic contribution due to lattice imperfection, and the second one is the contribution due to surface scattering, so tau I and tau s. So finally, considering these two contribution, we can write this imaginary part of this dielectric constant as epsilon 2 equal to omega p square by omega cube into tau I plus this tau s. Hence, from this equation we see that this imaginary part of this dielectric constant will obviously increase as the size of the nanoparticle decreases. So this imaginary part is directly related to the size of the nanoparticles. That means we say this dielectric property of nanomaterials is strongly size dependent, and this directly influence the real part of the refractive index, the extinction coefficient and other related dielectric constant like dielectric parameters like reflectivity and absorption through the materials, etc. Thank you.